Okay, that sort of worked. I had to fumble around and figure out what I was doing, but it sort of came around, I think, at least in my mind. So let's try a second pass. Okay, so we can construct z, okay, and we'll assume that I did that. And we can note, let's just make that z under addition. Okay, we can note that 4 axioms are satisfied. And you note in passing that we can make this our modus operandi. We can later think to do the rational numbers and think about those for a while. We can construct z plus, and we can note that 4 axioms are satisfied, and that if we do things like nz, where that's multiplication, we get a subgroup of this group of numbers. Okay, abbreviated numbers there. So, and the subgroup obeys the same axioms. Okay. Try to do this in an orderly fashion here. The axioms are associative. X plus y plus z equals x plus y plus z. Could attempt to prove that, but it's very simple. Prove it with our compass. There exists an identity, something like let's call it an e plus a. That's the identity. That's an element of our z, and that just equals a. And you can make it commutative if you like. And 3, there exists a inverse for every a is an element of z, such that a inverse, plus a equals 0. And that would just be a inverse is minus a, to jazz that up a little bit. And I forgot the first one here. For every AB in Z plus, A plus B is also in Z plus. So associative, existence of an identity, existence of inverse, and closed. So I think you could do with a CIA, closed, inverse, associative, and closed, inverse, associative existence of an E. K, CIA 0. Closed, associative generally next, identity, and existence. Oops, that's inverse, and existence of identity. CIAI. Okay, so do these ideas translate two finite groups. And you could say prior to that you do finite groups exist. Okay. Now we see that we have these infinite groups. Do we have finite groups? Look at a clock. We're going to simplify this clock a little bit. We're going to do, let's do that. 1, 2, 3. Look at a clock with 4-hour days. We could also do a 11 o'clock, normal clock, or 12 hours in a day, or 4-hour days. And note, can parse our Z into classes. Do 0 and then 4, 8, 12, then 1. See if I can figure this out. And you always add 4 to it, is that right? 9. This would be 2 plus 4 is 6. 6 plus 4 is 10. 3. Add 4 to it, you get 7. Add 4 to that, you get 11. Add 4 to that, you get 15. So you put all those into, if you like, parse Z into these 4 classes. And note or ask, do you get a group? Do you get a group? So that would be a finite group. So I do 0, 1, 2, 3. And this is under addition 0, 1, 2, 3. And we'll see if there is an inverse. Associatives are given as true for Z. Closed. Do I break out of this? Well, 0 plus 0 is 0. I get a 1, I get a 2, I get a 3. 1, 1, 2, 3, and then I go back to 0. 1 plus 3 is 4. And that's in this 0 group. Call this, let's do a double thing there. These are classes where you take 4 into n, you get a quotient with a remainder of 0, 1, 2, 3. Okay, so there's some hope that we could do this for any n. So let's keep on going here. So 2 plus 1 is 3, 2 plus 2 is 4, 4 is 0, 2 plus 3 is 5, 5 is 1. I can refer to my cheat sheet over here. And 3, notice that I just start earlier, the same pattern, 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. I get back to our number. I get an a plus 0 equals a, and 0 plus a equals a. So that's the identity exists. And I get, the bigger one is if I, in every row gets a 0, implies inverses exist. So CIAI, it's closed. I'm not breaking out of these things. It's has inverses, or let's make that the identity. It has identity, it's associative, and it has inverses, identity inverses. So that looks like a group. Try or contemplate subgroup. Let's say if I do 0, and I think I'm going to stop doing that, 0 and 2, I notice I don't break out, it's closed. Doing addition again here. 2 and this one, 2 and 2 is 4, which is 0. Closed, inverse, or let's make that a inverse. I get back to 0. From 2 I can get back to 0 by adding 2. 2 is the inverse. It's associative and identity. And 2 divides 4. In general, see if I can get back my numbering here. So that was 5, we're on to 6. Okay, 7. In general, per o'clock idea, I can make our usual 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 6, 7, 8, 9, 10, 11, mod 12 we'll call it. Okay, it modifies our usual integers by remainders with 12. So this would be 1 plus 12 is 13 maybe. 2 plus 12 is 14. 3 plus 12 is 15. I can now just add to the one before it. Okay, and then 13 plus 12 is 25. I imagine that's going to be 26. And note, two, let's see if this, 2x forms a subgroup, and 3x forms a subgroup. I stay within 2, I go to 4, I go to 6, I go to 8, I go to 10, I go back to 0. I start with 3, I go to 6, I go to 9, I go back to 0. So 2 divides 12, 3 divides 12, 4 divides 12, and 6 divides 12 all form subgroups. When you do addition, we'll do 3 under addition mod 12. And we'll see if this is closed. Existence of inverses, stuff like that. Well, this is going to be very easy. 0, 6, 3, 6, 9, 3, and then I just move that up. Same kind of drill. 6, I'm adding 3 to it, I get 9, I get a 0 there, I go back to 3. 6 plus 9 is 15, which is 3 mod 12. 9, 0, 3, 6. So each of these has an inverse, so I can infer. Associative closed, I'm not going to be able to break out of this, take any representation, so I suspect We're now at 14 minutes. Suspect for any group G, finite, let's do that one, any finite group, we had infinite groups, for any finite group G, a subgroup S will be such that the order of S divides the order of G. Okay, this is going to be harder for a different group that permutes a finite number of elements. This group consists of functions. Functions, 8, 9. So if I have 1, 2, 3, I can make the group 1, 2, 3. I can take 1, 2, 3. I can also do it this way. 1, 2, 3. 1 goes to 2 or goes to 3. 2 goes to 1 or goes to 3. 3 goes to 1 or goes to 2. That leaves 1 left of 3. Okay, 1 goes to 3. 3 must go to 2. 2 goes to 1. 1 must go to 3. Okay, let's see if I can get this. 3 goes to 1, 1 has to go to 2, 3 goes to 2, 2 has to go to 1. So I can write how 1, 2, 3 are permuted. 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. You take the first one, you do them in ascending order, 2, 3, and now you have to move to the next one in ascending order, that's 3, and you're left with 2. You can get the structure of this. I notice I get 6 of these, and I can combine them. 3 factorial equals 6, number of permutations of 3 objects taken 3 at a time. 6 of these, and I can combine them as with function composition. So let's say I have f composed of g does not always equal g composed of f. We'll look at that, but f composed with g is an element of the permutations. Okay, we'll attempt to show that. It's closed. And I can find, I suspect, that I get back to 1, 2, 3, existence of inverses. And associative is easy. Identity, if I make 1, 2, 3, meaning 1, 2, 3 goes to 1, 2, 3, I'll do it like that, equals the identity. Okay, so I notice in passing here, I can do this kind of thing. I can take 1 goes to 2, I can rotate, or I can flip. So can rotate or flip to see picture and infer closure. I'm always going to stay on the triangle, equilateral triangle. So I have 1, 2, 3. I do a rotation, say around this way. 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay, and then I rotate again, and that 2, okay, then goes to 3, 3 goes to 1, and 1 goes to 2. Okay, we call this, I think per Herstein, we'll call it psi. And then there's a phi, which flips. So I have 1, 2, 3, and I just flip those. Okay, and between these two, I'll be able to get all 6. Okay, notice that if I do 2 and I flip these, I get 2, 3, 1. Okay, and that's a repetition there. And generally, I notice that psi, the rotation, is such that I'll get something new as psi squared, but psi cubed will get back to the identity. I rotate once, twice, and when I do 3 times, I get back to 1. Okay, and then if I do a phi, phi squared is just I. The question becomes, what is psi composed with phi? And I think we're going to find that that's not equal to phi composed with psi. Okay, that's 22. Okay, I think we're going to make this a little bit easier to follow here. I'm going to make our psi just f. And I'm going to make it very clear what this means. That goes to x2, so f of x1 equals x2, f of x2 equals x3, and f of x3 equals x1, just to do the familiar. Okay, and then, okay, that should take care of that. We'll make g of x1 is x1, g of x2 is x3, and g of x3 is x2. So this is the rotation, and this is the flip. Okay, can we get all 6 from these? So notice that we'd have a, call it F1, F2, F3, F4, F5, F6 for all the functions there. I think I might change this around. And right, this would be F1, F2, F3, F4, F5, F6. And these are defined as Fi equals, it operates on 1, 2, 3, and it does various things. So you have a total of 36 combinations of these 6 permutation functions. Can we get all 6 from F and G? Question mark. Okay, we have that this is closed. And then how would we get to a subgroup? Get all 6 from F and G. We'll do one example going back to here. We'll do F composed of G. Where we recall F of 1, 2, 3 equals 2, 3, 1, and G of 1, 2, 3 equals 1, 3, 2. Okay, so I somewhat might work a little bit there. So if I do in the usual way, G of 1 is 1, so this is F of 1, and that is 2. F of G of 2 is 3, so that's F of 3. F of 3 is 1. F of G3 is 2, so that's F of 2 equals 3. We got 2 and 3, which is different than either one. Now, just out of curiosity, we'll do G composed of F and see what we get from that. So this would be G of F1. F1 is 2, so that's G of 2. And G of 2 is equal to 3. G of F of 2. F of 2 is 3, so that's G of 3. G of 3 is 2. G of F of 3. F of 3 is 1, that's G of 1, which is equal to 1. So we got 2, 1, 3 for here and 3, 2, 1 over here. Not, let's see here, not commutative. F or does not equal GF, where that's the operation of group. Okay, now here's where the crescendo takes place. I think this is 12. I think I give this up 12, 15, 14, okay, 15. Okay. Suspect, and we'll say it, suspect, take any finite set, perms, function perms, make a group. They obey the axioms. Okay, how could we show, and finite groups not like modulo n groups because don't commute. Okay. All right, so how could we show obey the order of a finite group divides the order of a subgroup divides the order of the group for which it's a subgroup? Hard. You see me with all of these things and trying to make a table for this thing. That's not going to be easy. You saw me do it. It took a while. To make one for the modulo n under addition was easy. The idea of abstract algebra is to use only the axioms, you could say if possible, to get both symmetric groups Km all perms on N and this group here, modulo N, at same time. Okay, and then we could, okay, that's going on 30 minutes. Okay, so we'll stop with that. That's a little bit better.